Hello and welcome. How are y'all doing today? You get a good 10 o'clock hour set of talks? One, two. Who went to two talks in the 10 o'clock hour? All right. I wanted to go to one of those. Who went to two? Who was out here with the vendors drinking? Hi, my name is Atlas. Nice to meet you. I'm happy to have you all here today. In case you're wondering, there are 120 seats here. There are 2 dividers with 4 heat exchangers and Wi-Fi, and so that's what I do before I give a talk. I own the room because it is my room, and if you give me any grief, I will kick you out. I'm just kidding. 2 exit doors on your right. In case of emergency, file out those doors and don't trample anybody. So this is an interesting day for me. They don't have a lavalier mic, but they have given me extensions, even though their GoPro is not going to like me. So today we're going to talk about heavily reverse engineering, heavily modified, or heavily obfuscated binaries, specifically for a car hacking modification tool. So a little bit about me. I'm a Jesus dude, father of 3 amazing kids, hacker of things, maker of hacks. I love making tools that make hacking easier, which is why I really love software reversing. But about 2008, I got wrapped into hardware hacking and all sorts of cool things. So a little bit more about me. Data telecom background, shifted into cybersecurity. CTF taught me that I can do a lot more than I ever thought possible. And then from CTF, got wrapped into hardware hacking, power grid, cars, medical equipment, aerospace things, and ... So who here's had that moment where they realized, holy crap, I didn't think I could do that? Can I have a show of hands who didn't? Oh, you don't have to, but truly, like, talk to me. For the last 20 years, that happened to me 20 years ago-ish. For the last 20 years, I've had great joy helping other people realize what they're actually capable of, because I realized in 2005, I had set these boundaries around what I was capable of, and self-protective. If I think that I'm only capable of here, I'll stop before I run into them, and then I won't be disappointed. But then I would have missed one incredible set of years. So love riding motorcycles and all sorts of other cool stuff. Swing dancing, Latin dancing. If you dare, this is a lot of information, contact information for me. I'll give you about 30 seconds to snap a picture, if you dare. Do, 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 do. So I got a chance to talk to some of you. Got a nice smattering of skill sets and interest level, or interests, not interest level. If you're here, I hope you better be very interested. So who here has ever had a car? The OBD2 port, onboard diagnostics, must be within reaching distance of the steering wheel. So that's why it's under wherever you're running your legs into it or whatever. And it is a way for mechanics to fix your car or diagnose your car. Actually, it has so many other purposes from that, including checking to see if your exhaust emissions are good enough and blah, 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 blah. Anyway, most often in recent years, these are basically a glorified CAN interface to many of the important systems of your car. And in order to interface with your ECUs, the electronic control units that control how your engine runs, whether your doors unlock or whether control your windows going up and down, or other things like the microphone and stuff. I skipped something that I really wanted to say, but I'll get back to it. In order to do this, you have a hardware tool that does the signaling. The hardware tool, either through Bluetooth or a wired connection, connects into a laptop most often, where some standardized set of software is installed, basically a standardized API for interfacing with cars. And then you install a third-party software. Most often, if it's a Ford, you download Ford software. If it's GM, you download their software. But there are some third-party aftermarket tools that allow you to interface with the car as well. They plug into this whole stack to talk on your car, your CAN bus interface on your car, most often. So this is a very valuable thing to understand. When this software talks to your ECUs, it is able to reprogram how the ECU works. Maybe flash firmware updates for your ECU. Program new keys to your car so that your immobilizer says, oh yeah, cool, he's actually in the car. And many other things, code execution. There are two ways that the industry is trying to protect this right now. There's an authentication that is now, it's brand new-ish in the last 5 years, because cars have a 5-year cycle. And before that, there was a security access mechanism. Basically, you get on the CAN bus, you send a message saying, I want to enter this diagnostics mode. And there's generally like 3. And then you say security access, which is basically a seed key exchange. Security access, the ECU sends you back a thing going, all right, here's some gobbledygook bits. Do the magic to it so that I know that you're okay to talk to. So this is the authentication mechanism that's been in use for 15, 20 years or more. So the authentication mechanism, the newer one, you'll notice there are hexadecimal numbers associated with this. So service 27, that's saying, this is my CAN message 27 that I'm sending. And that's how the ECU knows that you're authenticating using security access. Hex 29 is the new fandangled version, and it can include a lot more. Like before, it's just a certain size of random bits, blah, blah, blah. So the authentication mechanism, they allow for a lot more information exchange, and you can do cryptographic key signing type authentication. So we're not going to talk too much about that. There are ways to hack that, but it involves a different approach. So I set out, my team, after I left the Intel community, I joined Grimm and have been part of their cyber physical systems team for the last 10 years. And we have developed skills and abilities to hack all the embedded cyber physical systems. So started off power meters, because that's actually how I got dragged into hardware, but then the same concepts translate directly over to cars. And I've been playing with cars for a long time. I used to hate computers in cars because I wrenched when I was 16, and I still have that 74 Datsun 260Z. But figured out that the same things that we use to hack power meters applied to cars. Different protocol, different culture of people, maybe a few other things, but the microcontrollers are the same. The storage mechanisms are the same. The protection mechanisms are pretty much the same as well. So we did that, transitioned into automotive, then aerospace, medical devices, and all the computers that can kill you, basically. Cyber physical systems. So I started off with this idea, okay, I'm not. So by the way, I don't have a clicker, and I don't have a lavalier, but I still love to move around, so I'm going to go back and forth. I will say, if you have a hardware or radio hacking device, I did leave my clicker's remote control in there, if you want to try to control my slides. The clicker itself is broken, but I thought I'd throw that out there for you anyway. So we have developed this ability to interface with a bunch of different vehicles over the last 10 years, and to be able to set whatever security level we want. Why? Because my world revolves around remote code execution, and the easiest way that I've found to gain execution of code on an ECU is to put it into firmware update mode and say, oh, here's the code that's actually going to flash that. So we had a gap. One of the OEMs introduced a new method, and we didn't have it covered. So they send a key, we'd send it back an answer, and they'd be like, nah. Can't do it. So I jumped in, and I'm looking around for ways that I can easily knock out, and in a fun way, this new authentication or this seed key exchange mechanism. Ended up choosing a third-party tooling, which is why I'm feeling a little comfortable talking about it, even though I have tried to obfuscate everything possible about it. By the way, if you're expecting O-Day at the end of this, you'll be sadly disappointed because I love the community. But I will be teaching you how to go find your own O-Day, and that's actually way more valuable. So we'll just call it the binary file. It's an obfuscated PE binary. Anybody know what a PE is? So Windows executable. So on POSIX, Unix, Linux, it's basically ELF files. On Windows, they're PE files. You know them as .exes or .dlls, but actually the internal storage mechanism is PE. No dependencies. This means you run the program, it doesn't say, operating system, please load these kernel 32, user 32, blah, 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 blah libraries for me. Kind of does that on its own once it deobfuscates itself, but that's a different story, and that's pretty common. It's like reversing malware, but at the end of the day, if I let it slip and it runs, I don't get infected, the program pops up and runs like it should. So it started off, I don't know how much you guys can see this, but there's a push of an address location, and then a call to this other address location and return. This is the very entry of the program. That first thing called is literally a return, so it's basically NOP. And so when we get down to this other return, it just is basically a jump into this first location that we pushed onto the stack, blah, blah, blah. And it goes on and on and on in very nasty, gnarly, not very easy to reverse ways to do all sorts of weird stack manipulation things and basically deobfuscate itself in multiple layers. So it'll go blah, 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 and kind of be building the code that is deobfuscated. And then it'll jump into it, and it'll run that, and that will deobfuscate another layer of code. And after enough of these happen, you have a program, deobfuscated, running in memory. So I thought to myself, how do I do this in a way that is A, going to be fast? It was not, but that's a different story. I've used it for mentoring. I've used it for so many things. And B, I'm going to have fun with, and going to be able to build out a tool set, something that this is in my spare time, so I need it to be fun. So either I could be doing emulation of the code, and trust me, that's actually what normally gets me up in the morning, or we could try something special. Basically, let the program load itself, and then snap in, grab everything out of memory, and load it into a Vivisect workspace that I can then analyze. So normally, I would be talking about emulation, either QEMU or Vivisect's emulation built in with Vivisection. Something I'd like to throw out there that I didn't do, but gives hope that we'll always be able to do some cool stuff like this, is kernel debugging. If we get to a point where the idea of running a program and then debugger attaching to it and pulling everything out of it that we can analyze, if that ever becomes too much, and they somehow figure out how to keep us from doing that, debugging the kernel itself means that we still should be able to get in and basically do what we're doing. So we start it up, we connect to it with a debugger, grab all the memory out of it, and dump it into a file. Okay? For this, I used Vivisect's VDB, the vulnerability debugger. It has the idea of snapshotting. Basically, what VDB does is it attaches to a process. You say to dump a snapshot. Yes, I will get my words eventually. The queue kind of runs out of words, and so it throws out random words, kind of like listening to AI. And then we shit it out into a little V snapshot that we can analyze later, including processor state, so all your registers and your PEB and your TEB, if you're Windows people, PEB and TEB, basically every thread running on a Windows program has this little snippet of memory called the TEB, the thread execution block. And it gives context for that running thread. Inside of every TEB is a PEB, which is a program execution block, and it's like the centralized thing that every thread can access, every part of the program can access to gain knowledge about the program and actually tap yourself into NTDLL, which is a great obfuscation technique that malware uses. But so we snapshot, so we run the program, attach with VDB, and VDB has a command line interface as well as GUI. I like the command line interface for this because I don't need the GUI. And we just create, we attach to it, it spits out all the libraries that it has found. Now notice, there are no dependencies in the program itself, but once the program got deobfuscated, it then just loaded in the things that it wanted. It just hid it from you. And we say snapshot, and we create target.vsnap. And it goes through all the memory maps, shits them out into the file. My second favorite word is shat, so I'll probably find a way to use that too. So before this talk, there was no good way to load vSnapshot files into a Vivisect workspace. They've basically been somewhat separate, but equal parts of the Vivisect project. Done a lot of work to make this a reality. I've not gotten it merged into mainline Vivisect yet, but the Vivisection code should have it available in the near future as soon as I like the stability of the results. I'm a hacker. I just want the stuff, I want to do the thing, and at the end of the day, if 30 to 50% of it is garbage, but I don't need that 30 to 50%, I'm generally good, but I'm trying to get it so that it's actually 95, 99% good. So basically, we roll through all the memory maps that are in the snapshot. We load them into a Vivisect workspace as a memory map with the same permissions and whatnot. And that's the easy part. We then throw a little bit of the metadata like, hey, you know, here's the registers at the time of capture, blah, blah, blah. But then what? We had two different hard-fought lessons. I talk about myself in the third person plural because I run multiple personalities. It's not a disorder, it's a feature. Tried 3 or 4 different ways to do this. Some of them I'm trying to use as much code that's within Vivisect as possible because I don't want to do anything too much outside that I have to maintain more code. But at the end of the day, I ended up modifying the PE parser from Vivisect so that I could do exactly what I wanted. Yeah, you can look through that later. If you want, reach out to me. You got contact information for me. I'm happy to share it. Right now, this lives in a non-committed file called shit.py. It's where I keep all the real good gems that haven't been refined yet. Yeah, had some issues. I'll talk about the issues in a minute. So, who here's done a little bit of or a lot of malware reversing? Good. You'll understand a lot of what we're dealing with. This is just like malware. It's just, at the end of the day, they're not infecting your system. They're running a cool program. But they're trying to hide the thing that I'm after, they're trying to hide it from me. Fuckers. So there are 4 major ways that I've run into that malware obfuscates, and so do these tools. There's unpack and decrypt in place. So the program runs, it gets loaded at like 401,000 hex, blah, blah, blah. It runs, and it just kind of overwrites itself in place. I like that. That's pretty cool. Very efficient. And it doesn't have me tromping through all sorts of nasty places or extra programs. unpacking, decrypting into a new memory map. So you get running, it spins up, grabs a new memory map, and then just shits itself into the new memory map. Boom, we're done. Actually, the first one is harder to reverse because you start doing these things and suddenly you go back and the code's changed and you have to go analyze that code as well. From a disassembler's perspective, that's actually a bitch. The third one, and actually one of my favorite and coolest, is where it spins up another program or takes or attaches to an already running program like Explorer.exe and shits itself into there, spins up a new thread, because Windows is so friendly for remote debugging and thread manipulation, blah, blah, blah. Sometimes they'll just say, hey, load up Explorer.exe, strip out all the guts, and let's put our code there. So it doesn't even look different. And several other things, but these are the main ones. So I proved very early on, this is a decrypt in place or deobfuscate in place binary. The original, I don't know if you can read it, but it's 68019080 blah, blah, blah. And it turns into, at the same location, C70194OB79. Does that mean anything to you? It doesn't mean anything to me. But it does mean that it's writing it, it zeroes me in to where I need to focus. And when you're reverse engineering, one of the biggest helps and skills that you can develop is figuring out where to apply your attention. Most automated tools, at their very best, will point the skilled reverse engineer at where they need to look. It's not insert into a tool and the tool says, hey, here's magic. That works too, to a low percentage. But above that percentage, it takes a skilled reverser, not ChatGPT. So what do we look at? Okay, I got it chat into a nice Vivisect workspace. What do I look for? So obviously I'm interested in UDS, the Universal Diagnostics Service. That's the thing that allows you to put it into security mode and gain access to diagnostics. Searching for CAN-related things, searching for hex 29 and 27 as immediate values. So you've got your opcode, and it's a compare of this register with this hex 29. Like, that's very useful stuff. But here's the problem. I have the data shoved into a workspace, but I've got no analysis. Disassemblers use analysis entry points into a program that are clearly defined in the PE or the ELF or the Mako for Mac. Here are your entry points. This is x86. We have issues with not knowing where stuff is with x86. I don't even know where the strings are. So if I go into the strings window or I search through strings, they're not defined yet. See? So right here we have a, no, I'm on my screen thinking that you should be able to see what I'm pointing at. Oh, not going to help. Anyway, security array. I kind of like this. I want to know more about that. But Vivisect's like, nope, those are the bytes. 5, 3, 4, 5, 4, blah, So, I mean, there are some strings because metadata has strings attached to it when it loads in various things, but not very interesting. We got to figure out, where do I get a toehold? Where do I know to dig in? Security access is clearly something I want. So I run strings. Anybody here run strings? Actually, this is how I got into this madness. Running strings one time. Oh my gosh. So there are millions of strings. Some really aren't strings. Radix means nothing because this is actually a Vivisect workspace. So I ran strings on the workspace itself. So like where it is isn't going to make any difference. I just needed access to the deobfuscated versions because running strings on the binary didn't work at all. So once I get in there, I identify, hey, here's some cool strings over here on the right. I like, Wi-Fi IP, edition, product name, Windows. Yeah, extended license is active. Huh, that's really interesting. I know that this program can actually write new keys into the body control module so that you can start the car with your own key. So let's go check out extended licenses active, and I search and I find it. One result here at 708.120. Well, this is a slow process and wildly prone to being bad, and I'll tell you about that in a minute. So I wrote a tool within Vivisection, which is the Vivisect Plus. It's a plugin for Vivisect that allows me to do all sorts of hackery things that I don't have to have perfect, that are just for me, and if you want to use it for you too, don't complain. PRs are welcome. And I wrote in a scan for strings module, and I say, oh, okay, the first question that everybody should come up with is, how long does a string have to be to qualify as a string? So, hey, we get to set that. Default's 5. Do we search all memory, or do we start at a memory map and end at a memory map, and we only do within there? I needed granularity. I don't think I've gotten to the slide yet, but I'll breach it. I figured out where code was. I wrote tools to figure out where code was. Really cool stuff. We'll talk about it in a second. And overnight, analysis crashed because I ran out of memory, because it was all of memory. It wasn't just the thing that I was interested in. It had all of Windows, every library that it depended on. And it just, as soon as it hit there, it's like, woo, kernel 32, baby, yeah, let's do all this analysis. And basically, yeah. I have a 600 meg workspace file that takes 15 minutes to load. 45 if I do it over the network. It's bad. So I had to learn. So starting map, ending map, or starting address, ending address. I want to be able to limit. Do I apply the strings, or do I just spit out some results? And am I looking for ASCII or UTF-16? So I am not a GUI programmer. If you want a GUI programmer, I'm sure you know some. I am not one. But this does the trick. So I discovered strings. So I gave it some parameters. It went, and it started showing me strings. And I'm like, oh, this is looking good. With these parameters, I can have some faith. Because if you misidentify stuff in a workspace, you may call something a string that's really code, and it'll really screw with you later. When you want everything to be as exact and real as possible. So I figured out, discovered strings, and then I put in the specific memory address start and stop that I wanted to go for. Yes, apply the strings, go, and suddenly I had strings like security array and DPF, soot, PCT, CL, and OL, and SWDL sec level. Sec level is good, right? I like that. Problem now, like normally if I'm reverse engineering a binary, I go find a cool string, like access granted or whatever. And then I see what code accesses that string. What do you see right here? Nada. No code accesses that string, nothing accesses that string, but I have the string. Yay! Oh crap, okay. So x86 is a variable size instruction set. That means that you have instructions that are 1 byte in size, and you have instructions that are 15 bytes in size. All right. We're at a casino. Who wants to gamble? You don't want to gamble with something like this. Sorry, you have to know. Because as soon as you take guesses, you have multiple layers of things that you're reasoning about that suddenly you're not confident in the truth of what is what. So you have to start off with truth. This I know to be code. So how might we do that? Well, it turns out there are 12 stack areas, 13 actually, I think, in the last one that I did. Why is a stack interesting? I'd say no cheating, but it's right in front of your face. Because stacks store return variable, or return addresses. What's your return address? You have a program, or you have a procedure, function, calls into another function on x86. The call opcode takes the next instruction to return to and shoves it onto the stack. We have stacks. So we can just roll through the stack and find all the return codes. Oh, crap, but there's pointers everywhere. How do we know what's a what? Well, we go to the location that's pointed to by the pointer that's on the stack, and we disassemble it. If it disassembles to something good, okay, great. Let's back up, because the instruction that is immediately preceding must be a call, and it must end at that address. You following me? Does this make sense? So we back up. Problem is, calls can be multiple bytes too. Like there's a 2-byte call, there's a 3, 4, 5, 6-byte call. So we start at 2. Is it a 2-byte call? If it's 2-byte call and it ends and it started 2 bytes before, it's probably a pretty good thing. We'll call that code. We go back 3, we go back 4, go back 5. As long as it is a call within this certain range and it ends at the right spot, we're going to trust it. Okay? This is how I ran out of memory. But it worked. It frickin' worked. But it did take an 80 gig swap file and a dedicated machine that I could just let run for 15 hours. I don't know if you saw that. Yeah, 500 meg at the time. It's at 600 meg right now. It's insane. And also, with this much analysis done, many of the tools that I just rely on don't work. Because I rely on tools that emulate to a thing to the end, meaning I call kernel 32 and I stop. No, kernel 32 is right there. It just keeps going, and 15 minutes later I'm finding myself going, do I wait? Do I control C? We also found that this broke Vivisect Server. Anything this big didn't work. And I was able to find some bugs in Vivisect Server that I got fixed. So, yay! Got some good out of it at least. But it did take 45 minutes to load over the network. So we add in, I like things that are easy, and when I'm reversing, I love the challenge. I remind myself of the goal. I allow myself to sink in, to wallow in the bits, kind of, let them wash over me a bit. But with the hope that that time is going to be well spent. It will come with something. That means that I need to get rid of as much tedium as possible, because the brain drain, where my brain is actually spent and wrung out before I get to the thing that really gives me joy, no thank you. So write tools. That's actually why I write tools. So I added in something for vivisection to look through for stacks. Here's a starting stack, ending map. And for stacks, I'm also most interested in limiting what they're able to point to. Like, going through stacks, I don't want things that point to kernel 32. So restriction is good. Every so often, so that worked really, really well, but it didn't find me all the things that I really wanted. But I was looking through and just kind of exploring, like you do, around security access and some of these other strings. I just like to, it's all bits. I like to turn it into meaning, and that's why I do this. And the tools don't always get it. So I'm meandering around the strings, and I found a whole bunch of stuff that looked like this. AO835900. Oh, that's kind of a 3-byte string, but AO doesn't print well. 83 doesn't print well. 50, 86, 59, 00. Okay, 86 doesn't print well, but it's kind of like a string. null terminated string, right? Okay, look at the address to the left of it, 0075D288. I'm starting to see a pattern where 58 is repeated here, 59. Basically large numbers that share a whole lot of data in common at the upper realm with some variance at the bottom. Sounds like pointers. So I made them pointers. In fact, I created a pointer array tool for saying, hey, start here, go to there, make them all pointers. Well, Vivisect does the pointer thing, turns it into pointers, but then analyzes whatever they're pointing at. And I started seeing this name here, sub underscore thing, sub. Notice they're all starting with sub. That means they're a function. Every one of those is a function. I'm going, I like this. Pointer arrays, I love this. It's great. Oh, and by the way, security array now has 2 cross-references just by making this chunk of pointers above security array into pointers and the subsequent code that was identified. You guys with me here? I suddenly can back up a step and analyze the code that is accessing this string security array. And this is what C++ pointer virtual function tables look like. Who here's written C++? All right, good, a lot of you. So you guys are familiar with inheritance, object-oriented programming, inheritance, and all that stuff. So what happens is when you define a class with a set of functions that the class, okay, intro to OOP for those of you who haven't done it. Object-oriented programming is basically where you identify a thing, let's call it a ball, and you do some data around that pertains to the ball, and then you write some functions that do things for the ball. Like, it's all about knowing what to do for that object. That's object-oriented programming. You can subclass the ball and say, yeah, that bounce function that you wrote for generic ball doesn't work very well for a football. Things work differently. So I overload and write a bounce function for football that changes the dynamics, okay? In order to do that, C++ has to identify those functions as virtual, meaning I can replace them. And the compiler creates these cool, amazing gifts, godsends, called virtual function tables. So when you have a ball, you have a virtual function table that has all of the supported functions and pointers to other things too sometimes. And when you have a football, you have its own virtual function table that actually shares a lot in common with the original one, except where you overload something and you've got a pointer to a different function. So this that we're looking at right here is a virtual function table with functions that know all sorts of things to do with a ball or whatever the heck that thing is. So added in some new functionality, make pointer array. Allows me to start with a start address, stop with a stop address, or if I want, just say, hey, I know there's 20. Don't make me do the math. And stop if you run into a null pointer. Maybe you don't care. So again, I like flexibility. I like ease and lack of brain drain. So we started seeing vtable entries. And one of the cool things about vtables is that every function in a virtual function table, knows how to interface with this thing. In fact, in C++, you have a this pointer handed into every one of those doggone functions. If you want to figure out the structure of a C++ class, like if you make structs, C++ is basically structs with code. These functions know where all the fields are, so you can roll through this code and say, hey, that accessed this plus 16, okay? And it accessed this plus 15 at 1 byte in size. Oh, okay, cool, so I got a byte right there. And you can learn all sorts of things about what this is. So for example, the C++ class that is that is responsible for interfacing with this model year, model type of blah OEM. I'll just say Maserati because it's far enough away from the truth. And I'm not sure if they have OBG. Anyway. Another nifty thing about C++, especially Visual Studio C++ for Windows, the first entry is the destructor. Well, what do we know about destructors? Well, constructors are cool. Like, we do all the things. Nobody writes a destructor, right? Okay. Well, you should. Because as you build this object, which is generally objects within objects with strings and all the things, and it's good stuff from a reverse engineer's perspective, you may have to draw it out on paper, but it is an amazing set of information. The destructor goes through and it clears out everything, frees everything up. Like, if you want one place where you're going to get the most data about how that stuff is laid out, the destructor is it. It's that first entry. I'm working on code. I keep saying this. I'm working on code that does destructor analysis to spit out, a lot of good data on for you. It should be wrapped into vivisection. I got a shit ton going on in my life right now, so it's taken a lot longer than I thought. But that is coming. Constructors and destructors are amazing. And then based on what each function accesses, you can start to reason about what that function does. Then, as you're rolling through code that is not part of a virtual function table, you start to run into things like a call to malloc, and then writing of some pointer, a virtual function table pointer, into the initial portion, the start of, hi, are we back on? The camera shuts off every 10 minutes, apparently. It's a feature. What was I saying? Oh, so in normal code, not C++ code, or actually, unfortunately, most often, inside of one C++ object, there's calls to allocate memory for other C++ objects and stamping in other virtual function tables. But that's really good stuff, too, because now we can start graph theory. Anybody here like graph theory? If you don't, you should. Guilt, peer pressure, all that stuff. Graph theory, not the visual stuff. The idea of nodes and edges that establish and define relationships, that you can do sorting, and you can actually turn into visual things, because visual things are how I process the best. So there is code, creates memory, stamps a virtual function table into a particular part of memory. If you get other virtual function table things stamped into other parts of memory, you might find embedded objects. Find this a lot with strings. And the joy keeps going. So here is, I'm going to walk you through the destructor if you can read it. So the first thing, this is the destructor. It actually just calls free object if it's ready. And then if it's ready, it returns a 0. And it comes down and it actually decrements the reference pointer to that memory. And if it hits 0, it calls free on it. So this is cleanup code. And most of the destructors in this code look just like this. But that free thing, this is the actual cleanup code for the destructor. This is going through, I don't know how familiar you are with x86. This is 32-bit code. But you see things right here. So ESI is the this pointer at this point. There's a virtual function table number 6 with that address. I haven't gotten into great naming for this particular set of code yet. So it stamps that into the location. This is something that actually happens a lot more often than you'd think. If you say, I have a football, but I really want to call balls version of this, the C++ code says, oh, okay, balls virtual function table, just stamp that sucker in, call the thing, and then we'll stamp it back when we're done. So move EDI 16. Okay, so EDI register has the number 16 in it. Compare ESI 608 bytes into the this object. Okay, compare that against 16. Now, move something 7 into this local variable, and this compare does this this subtraction based. Yeah. Basically, if it is 16 or over, then it will call decrement and free. And if it's not, it won't. This is a C++ string. C strings, we all know, is character, 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 null, right? Null terminated string. C++, there is a structure that has size, potential size, and if the size is lower than 16 bytes, like there's room in this structure just to store the damn string. So this comparison against 16 is a dead giveaway. I think I'll be done. So it's a dead giveaway. If it's below 16, then everything is right here and we don't need to free this extra thing. Otherwise, if it's over 16, we have allocated the right amount of data in a buffer for that string, and there's a pointer where the string would otherwise live. So we see this throughout the deconstructor. Yada yada, move EBP. So part of cleaning this up is actually setting that counter back to 15 so that it never gets confused. It's kind of a safeguard, even though we're going to free it anyway. So we come down, 608, 604, ESI plus 608, ESI plus 604. These are all defining where shit goes inside the memory allocation for this object. So this is good telling stuff for nerds like me. I mean, let's be real. Come down, we do the exact same thing, compare against EDI, this 580, and we've got another string that we're freeing up. If it's bigger than that, we've call the free on that pointer that's stored there, otherwise just call it good. And then we find a call to another subroutine going, hey, here's something else. Go clean that out. And after a couple of iterations like this, we end up knowing where everything is, and in a lot of ways, find out what it is. So recapping C++ structure reconstitution, look for a whole bunch of pointers that resolved a code. XREFs to the start of a bunch of them. So when you go through the pointers, actually, there will be references to the start of that virtual function table in that code. So I just started off with a bunch of pointers, and at the end, I'm like, oh, there's a cross-reference right to this start of pointers. And that's how I know that's where a virtual function table lives. Or very likely. There's checking, but very likely. Analyze the first function for the destructor and go through the destruction process. Use graph theory and graphing. That is something I don't have time for. But what, you wanted to see the seed key exchange? Sorry, that's not how I roll. I'd rather teach you to fish and have you hacking for a lifetime. You're much better served. Go find it yourself. So the real conclusion, think outside the box. Don't be limited by your tooling. Make your tools better. Make tools. There's this delimiting factor in your self-development where you know tools to where you are the powerful one and the tools simply are things that you use to be powerful. Then go hunting. Imagine what it might look like. Sometimes it takes experience. Honestly, just jump in and let your brain meander around what the code is doing, because over time you'll start to figure out what things start to look like. Write some simple C++ code or C code, compile it down, reverse engineer it, try to figure out why it turned into the way that it did so that you can identify it better. Remember that you are the real power. Go forth and do great things.